So let me do this question here. It says a flat square coil. Let's just start drawing. Um, I've been drawing things horizontally, so let's draw this one vertically. I have a square coil of some number of turns, and when you're building it, it'll all be connected. But let me just, well, I guess I'm drawing it that way. So let me just label it. It's got some length on a side, 16 centimeter, and it's gonna have some number of turns. We'll say n, and I guess instead of saying 16 centimeter, I could have said the length L. Number of turns n is rotating in a magnetic field. So let's draw the magnetic field. And they are asking about the maximum EMF and all that. So let's draw magnetic field in the direction that makes most sense. And I think it's so that it's kind of perpendicular, at least the way we originally set up. And the way we would rotate this coil would be probably along this way, maybe. You can imagine an axis that bisects two of the sides, and it's gonna rotate like this. That'll be how it's rotating. So, and we are given the magnetic field strength, and it's asking if the maximum EMF produced in the coil is this. What is the angular velocity of the coil? So we are kind of turning it backward from what we might be used to, instead of being given all the parameters and then figuring out from the beginning to the end point, what is the voltage difference. We are actually being given this quantity and being asked about, okay, how fast is it rotating for this velocity to, for this voltage to be right. So I think for this question, you just have to I don't think there's any way around this. I simply have to write down an expression for the magnetic flux as a function of time. Once I have that, then I can use Faraday's law, which says that induced voltage is equal to minus of the time derivative of the magnetic flux. So once I have the magnetic flux as a function of time, then great. We just take the derivative and we are done. Or we are done with coming up with the equation out of which we can solve for omega. So let's first work on writing down that expression for the magnetic flux. So we know the basic definition of magnetic flux, that it's integral of B dA. Now, in the common situation where magnetic field is uniform and area is uncomplicated, you can basically have this be B times the area, where the area as a vector quantity is oriented along the direction of the surface normal. So here, let me write down the maximum magnetic flux that we could have. It'll be given in this orientation, and it'll be given by the magnitude of magnetic field applied times the area of the loop, so that'll be L squared, times number of loops. So it's because it's got the number of turns. If you're imagining the area, it kind of folds on itself in such a way that this single ray of magnetic field line should go through the surface n times. And I guess the easiest way to think about it is, well, this is like a square area of L squared times n of them. That's, I think, simple enough, gives you the right answer. So I'll say the magnetic flux maximum in this orientation is B naught L squared times n. So now I have to figure out, okay, so what's its time dependence? And I'll propose it's gonna look like this. It's gonna be a sinusoidal function, sine of omega t. It almost doesn't matter which one you use, sine or cosine of omega t. Now, B dot A, that itself will give you, B A cosine of the angle theta between the surface normal and the magnetic field. So here you can't just swap cosine and sine. It's fixed by the dot product, which uses the cosine of the angle between the two vectors. But because this is rotating, and that's what's producing the EMF, the motion induced voltage, or the Faraday's law voltage. They are the same. And the difference between sine of omega t and cosine of omega t ends up being a difference of, well, what's the time equals 0? At time equals 0 is the loop oriented in the way I've drawn. Then great, you should use cosine of omega t so that it matches the fact that at time equals 0, this is 1, so you are at the maximum flux. But what if your loop actually started out from an orientation like this? Then sine of omega t will work. At time equals 0, you will have 0 flux, and after some rotation later, you will have maximum flux. And all of this comes down to, well, which function you use doesn't really matter. You can use sine, cosine, either way the answer will end up being the same. Here, let me use cosine of omega t, just to be consistent with the picture I've drawn. So, using cosine of omega t. So that's going to be the expression for magnetic flux as a function of time. So, hey, do I want to know the induced voltage as a function of time? Great, I can do that. Just take the derivative. So, time derivative of b naught L squared and cosine omega t. I think I know how to take the derivative. I use chain rule, derivative of the outside and then the inside. Outside, derivative of cosine is minus sine. Minus is cancelled, so I get sine. So it's going to be b naught L squared n sine of omega t. That's the derivative of the outside. Now I need the derivative of the inside, omega t. So that's just going to give me a factor of omega. So this is the expression for the induced voltage, and if that's what they were asking, then, or that's the information we were given, then whether this is sine or cosine would matter. In our case, it doesn't, because they are relating all this with the maximum EMF, the peak voltage that we'll end up producing. So if we are looking at the maximum EMF, then we induce the maximum. It's basically all the factors except for sine of omega t, which will max out at 1. So everything else, b naught L squared n omega, is going to give you the maximum induced voltage. So you take this, solve it for omega, that's going to give you the answer for omega. And omega should already be in units of radians per second. So doing this algebra in my head, omega is the V induced max divided by b naught L squared n, in this question, n matters, number of turns. So let's see what that looks like. It's induced to maximum voltage. Gotta do it all from up. Induced maximum voltage, 30 millivolts divided by magnetic field, 0.05 Tesla times the length of a side, 16 centimeters squared, times the number of turns, 30. So that should give me an answer in inverse second, and I recognize that as radians per second. And radian revolutions, these are not real units, so they won't pop up. You just have to know from context. Was it radian? Therefore, I can just type it in 0.781, or was it revolutions? And I need a factor of 2 pi to make everything come out right. Pay attention to the context, and I think you should be able to figure it out.